So yeah, Georgia, you can start recording. Sorry. So hi everyone, welcome to the data science seminar. It's a great pleasure to introduce Nadav Dym from the Technion in Israel, and he's going to talk about efficient invariant embeddings for universal equivariant learning.
Yeah. Okay. So thanks for the introduction. Yeah, so feel free to ask any questions whenever, please. Okay, so let's get started. So first of all, let me acknowledge my collaborators. So Stephen Gortler, who was in Harvard. This is not a very recent picture, but never mind. And Tal and Sneer, who work with me in the Technion. Tal is a postdoc, Sneer is my master's student. So anyway, okay, so basically this is going to be a math talk, but a little bit of motivation from invariant machine learning. So here we have a sort of simple machine learning task. We want to learn a function from examples. The examples are images, and we want to solve a classification task, right? So it's pretty standard. So you can frame this as a supervised learning task where you want to find, you don't know this function f, you want to look for a good approximation in some hypothesis class h, which is some function space, right? And for this type of task, the sort of standard choice, or one of the standard choices, is convolutional neural networks. Okay, why is this a good choice? One of the things that people could argue is that it's good because it respects the symmetries of the problem. So, right, so we know that if you translate, and let's say apply some translation to the image, that shouldn't affect the result. And that symmetry, that invariance to translation is sort of hard-coded into convolutional networks. And based on this success, people have suggested in the last, few years to try to import this success to other domains. Okay, so for a given task, try to find out what its symmetries are and use them as an inductive bias to sort of inject them into the hypothesis class you use. Okay, right. So that's the general idea. So if I know that the function I'm looking for has some invariance, I want my function class to have the same invariance. So, okay, convolutional networks are one kind. There are many other examples. Maybe the most famous one are graphs, graph neural networks. So graph neural networks, you have many things can be modeled as graphs. A very flexible framework, and graphs have a certain permutation invariance. So if you change, the order of the vertices, that shouldn't really make any difference, right? So let's say here, so you see you have on the top left and top right, it's the exact same graph, but the orange and yellow are replaced, the order is replaced, that shouldn't matter. Okay, that sort of induces the two different adjacency matrices that these two graphs have may look somewhat different, but then they describe the exact same thing. Okay, so, and indeed, typically graph neural networks respect permutation symmetry. Another type of invariance, which we'll focus on today, although another kind of data, which we'll focus on today, although the other types are also relevant, are point clouds. So what is a point cloud? So at least a sort of geometric type point cloud, you have a bunch of points in 3D, and and they represent some shape. That's the sort of standard thing. Okay, so our notation for that is we have capital X is the the whole thing, and little x1 to little xn are the endpoints. Each one of them is an R3. Okay, and then you could have, so this is a pretty common way to represent shapes. And then you could have, let's say, a classification task where you have many point clouds. and you want to, okay, you want to classify them. So let's say you want to say that tables are tables and the chairs are chairs, right? And that has symmetries of its own. So one type of symmetry that sort of stands out from this picture is orthogonal invariance. So if you apply some sort of orthogonal transformation to the chair and you turn it around, you do something to it, it's still a chair, same thing for the tables. So you'd like your hypothesis class to be invariant to that. Okay. Another sort of variant of that, so it's almost the same thing, is sometimes you want to only allow you or only consider special orthogonal transformations or rotations, in other words. Okay, so the only difference is here the determinant must be 1. Sometimes, yeah, okay, and you know, OD also allows determinant -1, also allows reflection. Okay, so that's one type. Another type is permutation invariance. So, okay, so basically we have here shapes that are beta style of lots of points. And the order in which they come is somewhat arbitrary usually. And if you change, let's say, the first and the second point, shouldn't make any difference, still the same chair, etc. Okay, so this is another type of symmetry. And then at the end of the day, so sometimes we would like to think of each one of these symmetries on their own, but at the end of the day, maybe the most natural thing is to take both of them into account together. So we have some action of a rotation R and a permutation sigma, and that rotates, changes the orders, etc. Okay, so that's various things. This type of thing has several applications. So we spoke about, you know, there's sort of the things like this, which are more like computer graphics type vision type thing, or 3D models of whatever. Some nice scientific applications, for example, a regression task in quantum chemistry. So molecules are sort of essentially a point cloud. There's also some sort of graph type information usually between each two molecules. There's some sort of edge. And you could want to compute some function on the molecule. So here's one common example is you want to, you know, compute all kinds of chemical quantities of the molecule, like its energy and all kinds of things, which I don't really claim I understand very well. And usually it's done using a sort of very expensive simulation process called DFT. And you could hope that maybe a neural network could do the same thing much faster. But you know, once it's given enough DFT samples and learns how to do it. That's one application. Another application is for physics simulation, where let's say you can think of the point clouds as n particles. In this picture, you have 4 particles. And let's say you know where they are at time tau equals 0. And then that's capital X, your first point cloud, and you want to know where it's going to be at time 1. That's Y. Okay, and basically, again, so you could maybe run some physical simulation, but maybe that's expensive. So you want to learn this function f, which is basically projection and progression in time. And this is, okay, so this is actually something called an equivariant function. So it's not really invariant. What you'd expect to happen, right, if you apply some sort of rotation here, that should affect the output in the same way. Right? You're basically like just changing coordinates. Similarly, if you change the order of the points here, that should change the order in a corresponding way in the output. So that's a somewhat different thing. And we're basically going to focus mostly on invariance today, but equivariance is also important, so it's worth mentioning. Okay. And then, okay, and basically, so again, so this is a sort of rather active research area, and specifically for point clouds, which will be the examples we focus on. There are a lot of works also on various ways to build point cloud networks, which are permutation invariant, or also rotation and permutation invariant, et cetera, et cetera, et cetera. Okay, so that's sort of from the maybe more practitioner point of view. From a theoretical point of view, which a theoretical goal which one might want to address is to try to build these function spaces which are invariant to whatever, permutations, rotations, both, in a way that they are universal. So that means that not only they contain only continuous invariant functions, but also they can approximate any invariant function. So, right, so that's sort of what this means, right? If in analog for pretty well-known theorem that says that any continuous function can be approximated by fully connected neural networks. So here you have an analog of this question. You're looking at continuous invariant functions, invariant to some specific group action, and you have some architecture, some function space you come with, and you'd like, and all these functions are invariant. So by construction, they are only inside this green blob. They only contain continuous invariant functions, but you'd like them to be able to approximate all of them. Certainly, they cannot approximate continuous non-invariant functions, and you wouldn't like them to. So that's the sort of variant we're talking about. Yeah, I know. Questions up to now, maybe? Or, okay.
So, yeah, so if people have questions, they can type them in question and answer box. Let me ask you, because you asked for a question, I have a few things that came to my mind just to be sure. You had an example of the molecules, and you think about them as point clouds. And, for me, they're just graphs with features. I'm not sure why what is special about thinking about them as point clouds.
So certainly they also are graphs with features, but also sometimes you're also given the 3D coordinates of the atoms in the molecule.
Okay, I see. Yeah, I know. But there are some examples like this, right? But okay. And another small question, you talk about rotations, but actually we probably should consider Euclidean motions, right? Like you also care about the shift invariance, right?
Yeah, that's a good question. So for the questions I'm going to discuss, you usually can just centralize the point cloud and then forget about the shift. And then alternatively, I either talk about translations and then say that's what I'm going to do, or I just don't talk about it. Yeah, okay. But you could just assume that I centralized and then get rid of that. Okay, thanks. Okay, so moving on, I guess.
There's another question.
Yeah.
Does the top bar notation used in red indicate the closure of sorts on the space of function like topology?
Yeah, that's what I meant, but it wasn't meant to. I didn't intend to define it very clearly, but yes, I mean you could invent. Let's say these functions are defined in some compact set, and then the closure is the uniform whatever, respect to the uniform norm. Okay, so moving on. By the way, also what's the time frame? Till what time?
So it's better to end by 2:15, but we have 10 more minutes for questions. So if you need it, you can end at 2:25.
Yeah, okay, got it. Okay, good. Okay. So right. So we defined the mathematical goal, right? We want to approximate continuous invariant functions. We'll make some assumptions. Okay, so these are generally going to be too strong for everything we're saying, but it will be convenient to assume this and not, jump around making new assumptions all the time. Okay, so we're just going to call this nice. We have a pair G and V. V is a real finite dimensional vector space. Okay, so Rn or some Rn times m or something like that. G will be a compact subgroup of GLV. So basically, that just means linear transformations, and it's a compact group of linear transformations defined in V. And also we're going to assume that the map that takes G comma V to GV is polynomial. Okay. So just, going back to our point clouds, which we said is going to be what we're going to be focusing on. Okay, so there V is RD times N, and G would be OD times SN, or SOD times SN, or only OD, or only SOD, right? Any case, so this is some sort of matrix space. Okay, so V is a real finite dimensional vector space, and G acts on V via this action over here. So you take your X, which is the element in the vector space, and you multiply from the left by rotation, by the right by permutation. So, essentially, as a function of X, it's a linear function, and it's a polynomial. So certainly all the actions we described before are within these assumptions. Okay, so those are going to be our working assumptions. Okay, and given these assumptions, so then basically the question we're asking is, how can we, characterize all continuous invariant functions, for, let's say, in general, any nice, VG pair of group actions. And the sort of standard approach, which was formulated very nicely by Yarotsky, although it was also used by others, is to use this theorem by Hilbert, which says that if you have V and G which are nice, again, you can assume less, then there exists a finite number of invariant polynomials, F1 to Fn, such that all invariant polynomials are basically some polynomial function composed with these F1 to Fn. Okay, so these are, essentially this means you can make any polynomial you want just by taking these n functions and multiplying them and taking linear combinations and stuff like that. Okay, and algebraically, you can think of all invariant polynomials, they are basically a ring. And these functions are called the generators of the ring. So and basically this is a type of function, this type sort of an algebra type theorem, which says that this type of ring has a finite number of generators. Okay, so that's nice. So okay, what does this basically tell us? Okay, so where this is going is the following corollary, which you can prove, which says that okay, you want to approximate some continuous invariant function f, and you can do that on compact subsets by composing these generators with a neural network. Okay, so the idea of why this is true is that you can show that any continuous invariant function can be approximated by invariant polynomials. So that gives you this, and then you can approximate the polynomial p here by a neural network, because neural networks can approximate any function, and that's the way it goes. Okay, so that's an argument, and so basically this thing should work, for any right nice pair, nice group action. Let's call it that. Okay, so that's good news. What are possible issues with this? Okay, so one issue is one could wonder if you actually can explicitly compute the generators. Okay, so we know in theory that they exist, but maybe we don't know what they are. That usually is not an issue, or often is not an issue. Often we do have these things. There's also classical results in invariant theory, which for various pairs of VG, we have the generators. It's called the first fundamental theorem for whatever, OD, SOD. So we have that. Another question you could ask is how efficient this is. For example, how does capital N depend on dim V? Okay, so how does the number of generators depend on the dimension of the data, basically, right? The dimension of this vector space V. And the bad news is that this is often very bad. Okay, we will see examples soon. Okay, so that may be the main point, or the main disadvantage. Another question you could ask is whether you really want to use polynomials for approximation, right? So we're making a sort of attempt here using a neural network to be modern and use what people use, but these polynomials are not something that are very often in use in practice, you know, probably for good reason, but we'll see a little bit about that later. But for now, let's mostly ignore that point. Okay, so let's just see. Okay, so various actions of point clouds. What is the number of generators? Okay, so okay, so we have group action on RD times n. I think usually if d is much smaller than n, because in many applications d is 3 and n is maybe 100 or 1,000 or 10,000. Okay, so for the action of OD, you get n squared, which is not great. Again, so my frame of reference would be that I would think you'd need something like n times d or hope. So we'll see why I think that. Okay, for SOD, you get a pretty big number, n squared plus n choose d. For SN, the same. For these group actions, I'm not sure if we know what the number of generators are. At least I don't. Okay, but in any case, for the first three examples, the cardinality is not great. Okay, and this sort of led us and also some others to discuss the idea of, instead of using generators, using something called separating invariants. Okay, so these are some recent advocates for this idea in the sort of machine learning theory type world. Okay, so what is a separating invariant? Okay, basically separating invariants, there's plural. We have a finite number of functions, h1 to hm, which are all invariant. And also they are separating, meaning that if for some v and w, hi v equals hiw for all I, then necessarily w equals v. Okay, so this is sometimes also called a complete set of invariants. It means that you know, these invariants basically tell you everything about your group action, all you need to know. Okay, so let's just see an example. So here, okay, here's one of our point cloud examples. A simple point cloud, 2 points in R2. You have an action of the rotations, orthogonal transformations here. You just apply this orthogonal transformation to x1 and x2, right? And then, okay, so for example, you know, here are 3 pairs of elements in the space. The 2 blue points or the 2 green points or the 2 red points. And you can see that the 2 blue points and 2 green points are related by a rotation, basically, right? But the 2 blue and the red are not. Okay, so there's not, you can't find a single transform rotation that takes both of them, both blue to both red. Okay, so that's the way the group action works. What invariants can we think of for this type of action? Maybe are we allowed to ask questions to the crowd? Is that legal?
Sure, and people can type answers in the chat box, for example.
Okay, let's see if that works. So right, so the question is, what invariants are there for this action? You know, what seems natural? Okay. So fine. So I'll suggest what I think seems natural. So okay, so one thing. Okay, so one thing you could think of is, let's say, norms, right? So you could take the norm of the first point and the norm of the second point. Those are still not enough. Okay, so in terms of norm, all the points basically we drew in the circle here, all blue and green, they all have the same norm. So that doesn't separate, let's say, the blue from the red. But if I add also the distance between the first and second point, right? So then I can tell, right? So this is also invariant, and if according to these 3 invariants, I can already see that the red and the blue are not the same, right? Because the difference between x1 and x2 here is much bigger than here. Again, essentially, these 3 invariants are separating invariants. Okay, so that's the definition. Okay, essentially, we want to say that separating invariants are going to work better for our purposes than generation. So what we need to say for that? The first thing we need to say is that basically they can replace generators in this approximation theorem we saw before, right? So instead of saying that these functions are generators, we want to say that they are separating invariants. And we'd like to say that you can write any function as a neural network or some continuous function composed with these separating invariants, and that happens to be true. Okay, so that's also, it's not so difficult to see. It's probably not, you know, like this, but I think with a pen, and it's not so difficult to see. So that's the good news. Okay, so certainly they can do just as well as generators in terms of what we want to do. Another thing that's good to note is that generating invariants are separating invariants. So essentially, being generating is like a stronger property. But most importantly, in terms of cardinality, you can actually prove that there always exist separating invariants whose dimension is twice the dimension of V plus 1. Okay, so that is significantly better than what we saw with the generators, where the number can sort of go wild and isn't contained. There's no control on the number of generators. Okay, and here's a remark. So the remark is that when you look at the proof, essentially it's sort of constructive in a way. So the idea is you can take, let's say you know that you have any finite set of separators, for example, the generators, right? So we know that there are generators, a finite number, maybe very big. Then you can just project them down. So you can make new invariants by taking linear combinations of the generators. And if the number of linear combinations you would need is this number, just twice the dimension. So you can sort of, as a post process, apply a linear projection and get a smaller number. Okay, so here you have your V, you compute all the generators, then you apply a random linear projection, you get this. Okay, so that's okay. So algorithmically, I mean, that's constructive. Algorithmically, it's worth something, maybe, but it has a clear disadvantage, which is that at the end of the day, we have to compute all the generators, right? So that's not great. Okay, so what we can say from at this point, right, is for all our group actions we discussed, the number of separators we'd expect would always be 2n times d plus 1, because that's, okay, the dimension of our vector space is d times n. Okay, so the number of separators is certainly better than the number of generators. In terms of complexity of actually computing each separator, so maybe right now we're not doing much better, right? Because we just had to compute all the generators, and then, you know, if you just, you know, if you want to just count how much it would cost you to compute a separator by linear projection, just the projection itself will cost order of the number of generators, right? So the complexity is certainly larger than the number here. Okay, so that brings us to the next step, which is what we want to do better. So we'd like to actually be able to compute these in a more efficient way. And okay, so our method for that comes from phase retrieval. Okay, so maybe a short review of what phase retrieval is. So in phase retrieval, we have a complex signal in Cn. And we have some linear measurements, which are typically the Fourier transform, but maybe not. Okay, you have some linear measurements. In general, this will be a complex number, but then you only get its magnitude or its magnitude squared. You don't have the measurements themselves. And from these measurements, you'd like to somehow reconstruct the signal. Okay, and this is a very sort of important problem in signal processing. And this problem has some sort of invariance built into it. So you can note that if you multiply this signal z by a global phase, so by some phase factor, which is applied to each coordinate in the same way, then the magnitude will not change and exact same measurements. So you can really only hope to reconstruct the signal up to a global phase factor. Okay, so that's the best you can do. So essentially what you'd like to do is to say that if two different signals have the same measurements, then they're related by a global phase factor. Or in other words, what you want to say is that your H1 to HM are separating invariants. Okay, so maybe it wasn't phrased in this way in the past, but that's what you're actually doing. Again, a very famous theorem in this setting is this theorem by Balan, which says that, and others, that says that if you have 4n minus 2 random linear measurements, then this process is indeed separating, or is, okay, so these 4n minus 2 measurements will determine your signal uniquely up to global phase, up to symmetry. Okay, so that's that. And in terms of the actual number, so you note that, okay, so 4n sounds like 4 times the dimension, but really we need to think of Cn as, well, by the way, there's a mistake. This should also be Cn, sorry. So we need to think of Cn as a 2n dimensional vector space over the reals. And then the cardinality we're talking about here is 4n minus 2, which is similar or a little bit better than the 4n plus 1 we talked about before. Okay, so it's again twice the dimension of v, plus 1 minus a little bit. Okay, so essentially it's the same type of result we had before. Okay, but we'll see that it sort of gives us a more efficient. What's sort of crucial here is that the measurements we're talking about are basically polynomials, not only in the z, but also in these parameters w, right? So we have a sort of continuous family of invariants, and then we're going to be able to say that we can randomly choose some of them. Okay, and now let's see what you'd get if you talked about generators for this phase retrieval problem. Okay, so what does that even mean? Right, so you have this group action of S1 on complex vectors, right? So you multiply complex vectors by a phase factor. You can see that each one of these functions will be invariant, right? Because the phase factor comes, okay, so I take two different coordinates, multiply them, phase factor sort of cancels out. And these things are generators, and the number of generators is n squared divided by 2, more or less, right? So it's significantly worse than here, or off by a factor of n. Okay, so indeed here we have this difference. And the point is, though, we got here to 4n minus 2, and we didn't really have to go through going up and then going down, right? We just had some sort of other magical trick. And what we want to do is to try to take this trick and export it to other things like our point clouds, right? So this idea of generalizing beyond phase retrieval was done in several papers in various ways. But I think what we try to do, which I think hasn't been done yet, is we try to sort of have a general theorem for nice VG or for some sort of class of group actions where this trick works. Okay. And use it for our point cloud examples, which is what we are sort of specifically interested in. Okay, so how does this work? So we define something called a continuous family of separating invariants. It has to satisfy the following conditions. First of all, we have to have invariants. So this means that, right, so for all, basically for all weights or parameters w, the function described by these w's is G invariant. That's one thing. The second thing is separation. This means that if v and v prime are not the same, they're not related by a group transformation, then they can be separated by some W. Okay, so this is right. It's sort of the same as what we had before when we defined separating invariants, but before we would just right like we had a finite index set, and now our index set is a continuous index set. Okay, all the W's. Okay, and again, the example which we were talking about before, right, was when we had the action of S1 on C to the power of n, and these were our invariants. And it's pretty easy to see that for every W, this is an invariant function. If you multiply Z by E to the I theta, it remains invariant. See that separating is not a difficult exercise. Check. Okay, and then the theorem will prove is the following, that if you have V and G, which are nice, you have this continuous family of separating polynomial invariants. Okay, so for now we're assuming they are polynomial. Then you can, sort of randomly choose m different weights, and you get that these functions are separating invariants. Okay, so it's like you have a continuous family of separating invariants, and then you can just sample, not a very big amount, just twice the dimension plus 1, and you get a finite set of separating invariants. That's the general idea. And then one thing you could, okay, so that's the theorem. So some things about that. First of all, one thing you could wonder is whether the cardinality we get, okay, so we said it's not as good as phase retrieval got. And in general, it's true that this cardinality is not exactly optimal. And we're not so worried about that right now. The reason is that at the end of the day, I don't expect to get much better than the dimension of V, let's say, over G. Usually, up to a constant factor of 2, this is the best you can get. So I don't know, personally, not so worried about the exact constant numbers. In any case, let me say a little bit about the proof, or maybe I'll skip the proof, and then you can ask about it later if you want. So blah, blah, blah. Wait, let me say that. Jump forward. Okay, so I will say just one thing about, one sec. Okay, I think now we're stable. Okay, so right, so I just say, to make my conscience clear, that you can make this a little bit better in certain regards. First of all, one thing you can say is that the V, you don't have to really work with some vector space. You can instead, if let's say you assume your data lives in some low dimensional manifold, you can actually use that, and the dimension you get will be actually the dimension of the manifold. So this could be made the dimension of the manifold. Again, manifold has to be a semi-algebraic set, whatever that means. Okay, similarly, the polynomial assumption, which we mentioned before, maybe we don't love, can be replaced with a more general assumption called semi-algebraic mappings, which includes not only polynomials, but also piecewise polynomials, piecewise linear function, neural networks with ReLU activations, various things, not everything, but many things. And then you have to change your definitions here a little bit. It's doable. Okay, so in our paper, the full version, you can find it. But let me try to explain how this is useful in practice. Okay, so what I want to do in our remaining time is basically go over our examples, right? So one example we had is we have the action of orthogonal transformation on x1 to xn, right? Just you multiply all points by an orthogonal transformation. The generators there are sort of like we saw in phase retrieval. So you have the norm of each point, square norm of each point, and you have the difference between 2 points, square norm. Okay, so that's more or less n squared generators, right? And then you'd like to build a continuous family of separators. And what's nice, you can often do that sort of using your knowledge of the generators. So here in this example, okay, I'm going to build these continuous family by taking linear combinations of all the points and then taking the norm. Okay, and this is for any weight. This is an invariant function. And the reason this actually separates, you can always find some W that separates, is just because you can reconstruct all the finite generators from this continuous family using the correct W's. So let's say if you want the norm of the first point, you just take W1 to be 1, the other points to be 0. Right? Or if you want the norm of the first minus second, you take W1 and W2 to be 1 and minus 1, etc. Okay, so that's sort of the trick. And then what you get is that you can just take, more like 2ND plus 1 random weights, and these will be separating invariants, which ends up somewhat better than if you actually computed all of them and then projected them. Okay, so you're just doing some sort of random thing, but inside the norm. So that's certain gain you get for OD. For SOD, it's sort of nicer. Okay, so the special orthogonal group we said, right, is basically the same as before, just now we want our rotations we don't want only rotations. We want our R to have determinant 1. And then we suddenly get much more generators. So we have the same as before. These are still invariants, but also all of these are invariants. So if you take any D points from your n points, right, we're assuming n is larger than D, then their determinant will be invariant, because if you apply rotation, then the rotation will come out, determinant of R would be 1. So these would be invariant, and this happens to be D-generating or A-generating set. Okay, so it's a rather large number. Okay, but again, if you can build from these generators, you can build some continuous family of separators. Okay, so you have, as we had before, you have these weight functions, and then you can also add some matrix W here of the correct dimensions. It has to be n by D, right? And this will always be invariant for any choice of little w and big W. And from this choice, you can reconstruct all of these functions. So essentially, these continuous family does separate, and then again, you can, okay, the complexity of computing each one of these things is not too bad. And you get, right, for that you can, okay, computing each one is not too bad, and you don't need too many, only 2ND plus 1, and you're done. Okay. Okay, so sort of filled in this table, right? So we did 2 steps instead of, okay, so, right, so what we saw again is that the number of separators is small, but also the complexity is reasonably small. Okay, okay, another application, I guess maybe the last one for today, is permutations. Okay, so here, right, we said the action is you take your n points, you permute them, and then what's invariant here? Okay, so here let's talk first about the case when d equals 1. So we just have n scalar points, and they're actually we don't have any issues to pick with the generators, so they're good. There are only n of those, and the generators are the following. So one set of famous generators are symmetric polynomials. Another thing you can do is you can take the sum of all points, and then the sum of all points squared, etc., all the way to the sum of all points to the power of n, where n is the number of the points. Okay, so that gives you n invariants. And these n invariants are the generators. So in terms of cardinality, that's pretty good. Okay. The problem is when you go to, okay, now if I have n vectors in RD, then the number of generators is already rather large. Okay, grows. The bigger D is, the larger it is. Okay, and then again, so this, as we usually claim, generators we don't like. Instead, we're going to look at a continuous family of separators. And here we build it not like we did before by just sort of latching onto the generators, but we do the following. Okay, so what do you need to be a separator? Okay, essentially, you're assuming that you're given two instances, right? X1 and Xn, which are not the same, up to symmetry. Our symmetry is permutation. So essentially, this means that as sets, X1 to Xn are not the same as Y1 to Yn. Okay, and then, okay, so we want to say if we are given this, we can build some function which will separate them, a parametric function which will separate them for some choices of the parameters. So our trick is as following. First of all, you project down. So you take a d-dimensional vector, you apply a projection to all these points, and you can check that if the sets were different, then most projections will leave them different. Okay, so for fixed X1 to Xn and Yn1 to Yn, most projections will separate them. And now you have sort of a set of n points in 1D, and then you can use your separating invariant functions from before for 1D, which we said we already have with a good cardinality. We do that, and it separates because it separates. And then as a last step, also to sort of save storage, let's say. So, okay, here you have two vectors in Rn, and you apply a linear projection. And again, this will be separating for almost all vectors. So this is what you'd get. You build this sort of separating function, which looks like this. Okay, and this is like an Sn invariant and separating family. And again, okay, forget about that remark. Okay, so again, the idea will be that you can take 2nd plus 1 of these things, and it will work. Okay, so that gives us that. Maybe I'll take 5 more minutes. Okay, I'll cut down for my question. Okay, just to get to some pictures. Okay, so one thing which we didn't really. Okay, so now. Okay, we talked about various rotations, various permutations. If you want to do both of them together, you can do that. This is sort of a separate paper. It's a little bit more complicated. It's a little bit more pricey. It takes about n to the d. Okay, and then sort of what I want to do is just discuss, going back from the theory to the sort of machine learning motivation we discussed before. So you can then go to, okay, there are various architectures that people discuss for this type of symmetries. And you could ask some question. One of them is, does separation happen or not for these architectures in practice? Okay, so here you have, what we did is we took various data sets. We built rather simple data sets, you could say. You just take 2 point clouds. But they're hard to separate for whatever reason. And then you do some simple augmentations. You take rotations and permutations of them, which shouldn't change anything for invariant architectures. And you add some noise, and you just solve this binary classification class of, given a point cloud, did it come from the first one or the second one? Okay, so these are basically 1, 2, 3, 4, 5, 6, 7 different binary classification tasks. You see that the results are typically either 1 or half, and you see that different methods perform differently. Okay, and specifically, okay, so our point in this paper was to say that we can build separating function spaces for this thing, and this is what we get here. But let's say this would also be separating, and it's not perfect. And then there are other things. You can see that, okay, let's say this function space, with certain parameters should work. These we don't know why, but they do work. So it's okay, here let's say you have 2 different architectures where this one is actually more complicated than this one, but it does not separate as well. So there's a certain, what makes something separate well in practice, there's more to it than just whether there exists the parameter choice which works. And then on the other hand, you can also ask whether it even matters. Okay, so here we're going back to this molecule example we had before, where you have some sort of regression task on point cloud, which is also, there are also some graph aspects, as Gilad mentioned. And there we took a very well-known non-separating architecture, EGNN, and we sort of added a tweak that makes it separating or universal, to have the good theoretical properties we want. And, you know, sort of, you could arguably call this a win. It's not as convincing if you'd like. So, I mean, it is a win in the sense that, right, so black means you got a better result, a lower result. So we got, you know, in these 12 categories, most of them, we got better results, but the differences are not that big. It's like 10%, and here there's a pretty big loss. And at the end of the day, it doesn't seem to have, you know, this sort of theoretical improvement didn't seem to have a dramatic effect. So that's, you know, I think it's an interesting question, and you know, where this sort of theoretical type question should have the best impact. What we're sort of working on now is trying to look at autoencoders, invariant autoencoders, where you'd expect that you really need some sort of injectivity to get it to work. Okay, so then I think I'm going to skip this stuff. So.
Yeah, thank you, Nadav.
Thank you.
Yeah, if people have questions, please type them in the question and answer box. So let me actually, so yeah, this was very interesting. Let me ask you first, just to be sure, you said, you know, you don't see big improvement for this example, but I thought in terms of time complexity, you do have a big improvement, right?
So the complexity, yeah, so the time complexity improvement is in with respect to theoretical results. Here, this is like, you know, this is an architecture which actually you can prove that it's not universal. So it doesn't have to, it's, you know, it doesn't use generators to do anything. It just, you know, does something else. It's like, so this pretty simple message passing architecture, which only uses norms and stuff like that. And there's a paper which proves that this, you know, you can't approximate any continuous invariant function with this thing. But still, you know, maybe that's not so important for molecules, or maybe it's not important for, hopefully, I hope it's important for some tasks, but, you know, for this task, it doesn't seem crucial.
Okay, thanks. Yeah, another thing is, so yeah, I asked you before about the issue of the shift, and you said, you know, you can maybe estimate it and center the cloud point, so it's not an issue for you. But just out of curiosity, suppose I don't trust the centering and I want to build something for the Euclidean motions. So now I have a non-compact group. It seems to be a bit harder. Like, do you think there is a chance to do something for the, you know, including Euclidean motion or special Euclidean motion groups?
I mean, it ends up being the same. Yeah, so, right, it's true that one of the reasons I don't, you know, it's not compact, so it doesn't sort of fit in the framework. But usually you can just, you know, sort of put in, you know, xi minus xj everywhere instead of xi, and it sort of works. I mean, I don't think it makes it's that difficult to handle.
Yeah, yeah, I also kind of thought so. Okay, thank you. I say no. Jeff and Will need to leave pretty soon for a meeting, but if so, yeah, if they have question, let us know. But so I'll wait for a few more seconds. But I know people need to leave pretty soon.
Okay, no problem.
But it was a really great talk. I think there's some very fascinating things here. I want to follow up on this.
Sure, thanks.
Yeah, so yeah, thank you very much, and